Dear students, we'll discuss about the cross correlation and autocorrelation using MATLAB. Now, you have already studied what is convolution. Now, we will study what is correlation. So, now you know that correlation, in general terms, it is something like it gives the similarity. Correlation, it gives the similarity. Okay. Now, there are two types of correlation, that is autocorrelation and cross correlation. So now in autocorrelation is similarity with itself, and in cross correlation it is similarity between the signals. Now we will focus on understanding these two concepts using MATLAB. Now we will take autocorrelation. Autocorrelation. Why we have to use autocorrelation means we will try to find some similarity and try to extract some features. We'll take an example. Let us say I'll draw some signal. I want you to identify the frequency of this. So this is a sine wave, assume. This is a sine wave of peak to peak is 2 volts, and this is 0.5 seconds. This is 1 second. This is in time, in seconds. So what is the frequency of this? The frequency of the signal is nothing but one time period here is, from here to here is the time period. So frequency is nothing but one inverse of time period, that's equal to 1 by 0.5. That's equal to 2 hertz. It is very easy. So if the signal is very clear, it's very easy to even comment on the frequency of the signal directly. So let us say we had some signal which was corrupted with noise. So the signal was something like this. Now, what is the frequency of this? What is the fundamental frequency of this signal? If you look at this particular signal, you can say that roughly overall the signal is varying something like this. If you don't worry about these spikes, okay, in between, overall the signal is varying like this, and it is like 2 hertz signal. It is a 2 hertz signal. But what if the noise was much more? Again, I will draw one more signal. I will draw a signal. So assume this is a sine wave, okay, and the noise is so high. Okay, noise is something very high. So if the signal was something like this, okay, so if you did not have any reference, if you did not have a reference of this red curve, then is it easy to identify the frequency? So it is not possible. Okay. So what we do in correlation is, if the signal is x of t, okay, we autocorrelate. So autocorrelate, x of t with itself, then what we get? So autocorrelation equation is something like this. So Rxx, this is autocorrelation with x with itself, and this is the shift amount is given by, it is similar to convolution, x of tau h of t plus tau d tau for all values of tau. Okay. Now, it is something like this. In autocorrelation, what we have to do is we have to take the given signal, that is the noisy signal, and here it's not x h, instead it is h. X of t, because it is x with x only, okay, noisy signal, and it is a shifted noisy signal, So for different amount of shifts, what we have to do is you take the dot product, multiply element by element, or get that signal and get the area under that curve. Integration is the area under the curve. That gives the amount of similarity. Okay. So we'll understand with a simple example. What is the autocorrelation of a sine wave? So let us say my x of t is a sine wave like this. Now, x of t plus tau, that is when tau, we want x of t plus tau, When tau equal, the amount of shift tau equal, if tau equal to 0, x of t plus tau will be equal to x of t plus tau will be equal to x of t. So, we will be getting the same signal. Okay. So this is x of t plus tau, that is the amount of shift is 0. So this is t, when t equal to 0, x of t plus tau equal to x of tau. Yes, small correction. So here we have to shift or change the scale. So from t scale to tau scale. So tau scale, this is tau scale. So t is the amount of shift. T is the shift amount. And the scale is tau. On the tau scale, it is the shift is t. So t shift is 0. So 0 plus tau is x of tau. It is x of tau only. Now what we get is this signal. Now we, as per the equation, what we have to do? We have to multiply x of tau into x of 0 plus tau. We have to take element by element multiplication. We have to multiply this with this, and all these areas we have to multiply. So it is basically a sine into sine. Okay, it is sine x into sine x form. It will be sine square x form. Okay, so the resultant curve will be on the tau scale. So at the 0 instant, it is 0 value into 0 will be 0. So these extremities will fix. So this is 0. and at this one complete period, this is 0 value into 0 value is 0. Similarly at the mid value, mid value, and at this 90 degrees position it is 1 into 1, it will be 1 here. So if you have taken a sine wave of amplitude 1, okay. Now at 270 degrees it is minus 1 into minus 1, it will be again plus 1, it will be plus 1, okay. In between at sine pi by 4 or at 45 degrees it is 0.707. 0.707 into 0.707, that is 1 by root 2 into 1 by root 2 is 0.5. It will become, it will not be 0.707, instead it will be 0.5. So at this point it is 0.5. Similarly it is 0.5 here, and it will be something like this. The curve will be something like this. Something like this. Okay. Now the product value is this, but we have to integrate this for the entire duration. If you integrate the area under the curve, the area under this curve is the integration value. So integration value will be some number, some value v. Okay. Now we have to shift. This is a value at for zero shift. Now if you write the autocorrelation function on the time scale t, Rxx of tau, okay, Rxx of tau will be, for a shift of t equal to 0, we have a value v. We get a value v. Okay. Now, so your autocorrelation, complete autocorrelation depends on the shift value. That is, we have to shift, keep on shifting. Okay, t. Now, if we shift the signal, that is, let us say we shift a half cycle. If we shift a half cycle, so much if we shift, what do we get? So we get the signals look like this. X of tau will be like this. And X of, I will shift for a duration of t plus tau. So you are shifting for half cycle. So this time corresponds to half cycle shift. Half cycle shift. Then how will the signal look like? So we'll shift it like this. So we'll keep it as it is here. It looks like this. Now, what is happening is, we have considered only one cycle. So for one cycle, half cycle shift, so the half cycle is somewhere over here, we'll write, and full cycle is here. So for half cycle shift, now again we have to take the dot products. So in this time duration, the positive values of x of tau will overlap with zero values of x of this t plus tau, and that will be zero. And area under the curve of that product will be zero. Okay. So I'll write the product curve. The product curve looks like this. T, sorry, tau. All these are taus. Tau. So here it will be 0, up to here it will be 0. Okay. And then from this half cycle onwards again that will be 0. Only in between we have a negative half cycle overlapping with a positive half cycle. Therefore, here it is minus values into plus positive values will give a negative value. So just to plug in, we'll take the extremities. It is minus 1 into plus 1 is minus 1. So this is minus 1, and in between it will be some signal like this. Whatever is the curve. Okay. So it is something. Now what has happened to the amplitude? If you take the area in this curve, if you integrate, the area in this curve is some negative value. Negative value. Okay. So, and that is not a complete two half cycles. It is just one half. That will be something like half of V. So it will be minus V by 2. So we will represent that at this point the value will be not minus V, instead it is minus V by 2. Okay. Now, if we shift the second signal to full cycle, there will be no overlap. Okay. So there will be no overlap and it will be 0, and any further shift will give you 0 overlapping, and therefore the integration value will be 0. Okay. Now we can interpolate these values. Okay. And we can complete this. So initially we have full overlap, and later it goes on decreasing in area. It goes towards minus V by 2, and later it is decreasing towards 0. This is what will be the result. Now, if we shift the second signal to the left, we will get exact replica on the left side also. So we will get something like this. Okay. So this is the autocorrelation function. Now, what is the use of this autocorrelation function? Means, if we had some signal for which we don't know the frequency, then we can take, so if we have a signal, we have some signal x of t, so we can take autocorrelation, and we will have Rxx of tau, and why these peaks have created? This peak is created due to zero shift. Whenever there is zero shift, complete overlap will be there. Therefore, we get this max. And why this negative peak created? Because the positive things overlapped with the negative things, and we got this. Okay, we can identify these peaks, and so from this we can identify the peaks and measure the distance or the lag, time lag. So what is the time lag? So from here to is a time lag. So the time lag corresponds to the periodicity. in the signal, in the signal. Okay.